Okay, this video we're talking about writing node voltage equations in a little more detail. There's some things that you have to recognize when you see a circuit to be able to apply node voltage to that circuit. All right, so here's the circuit we're going to look at. It's reasonably big so that we can get in several different cases that I want you to be able to handle. All right, so let's talk about this. Let's keep the original here and I'll make another copy. Okay, so copying this, we get this circuit, and we need to figure out what are we going to do in terms of defining the nodes and choosing a reference node. Okay, so this class is not exclusively about circuit analysis, so we just want to give you a taste of how this goes. There's a whole circuits course you take, whether you're electrical computer or mechanical, you take a circuits course. But we want to give you the idea of how to get started with this. And so typically you choose the reference down at the bottom of the circuit. And I've already done an example where you can redraw this circuit where everything connects to a common point. I think we're past the need for doing that. I think that what you realize is that if this is the reference, we would call that 0 volts. That 0 volts applies over here. It's 0 volts here. It's 0 volts right here. There's 0 volts with respect to the reference at this dot. All right, so you get the idea. As long as there's just a wire connecting those points, it's at 0 volts. Okay, so let me undo those. All right, so let's use that as the reference. Next, we need to choose some other nodes, and remember, nodes are where 2 or more branches come together, 3 or more branches come together. All right, so I'm seeing a node right here. I'm going to label this with a different color. I'm going to call that VA. I'm also seeing a node right here. I could label that, but what I notice right away, because I've done a lot of these, is that if this is 0 volts, here's this dot, that's at 0 volts, and then on the other side of the voltage rise, this is a voltage difference of 40 volts. This dot would be 40, which makes this node 40 volts. So it's not really unknown. Okay? So that's one of the things you need to be able to see. All right? And so moving forward with that, we'll call that node 40 volts. Then we also know that here's another node. We can call that VB. All right. And then I see another place where 3 or more branches come together. This would be VC. Okay. So we have 4 nodes here, but 3 unknown nodes. One of them we already know is 40 volts. Okay, so from here, what we need to do is write node voltage equations. And let's get started at different nodes, all right? So I want to show you what the problem is. If you just randomly start and you say, well, I want to write the node equations at this node, you immediately run into a problem, okay? The problem comes from this branch. I don't have a resistor anywhere in this branch, and so I can't use Ohm's law to find this current I alpha. All right, I could find I alpha eventually if I know, I beta and I gamma. All right, but without having a resistor in that branch, it makes it harder to apply KCL at that particular node. All right, so I don't expect you to be able to handle all the cases for node voltage, all right, but if this one comes along, I would think, I'm hoping you would recognize there's no resistor in that branch. I can't write a node equation there, okay? So let me undo all that marking and we'll move on to a different node. Okay, so let's take a look at node VA. Okay, So at node VA, if I was going to find this current, all right, at node VA, I would look at these three currents, okay, I1, I2, and I3. All right, I think I1 is pretty straightforward, and if we wrote node equations at node VA, then what we're looking at is I1 plus I2 plus I3 equals 0. Okay, so let's start taking a look at this. All right, if I try to slide the dot for I2, let's look at I2 in particular at this point. All right, this dot I slide up to be 0 volts. This one I slide down to be VA, but I'm not across any single one of these resistors. All right, and so I really can't calculate the current unless I do something. Okay, and I think what the obvious thing to do would be to combine these as an equivalent circuit. The equivalent circuit would be just put these things in series and combine them to a single resistor. If I did that, then I can put a dot on either side of the only, well, I would know the values of the dots on either side of a resistor, and I could calculate the current I2. All right. So I'm going to hold off for now because I want to talk about a different spot in the circuit too. All right. When I get around to finding the current here, I'm going to call this IC. Okay. If I was looking for this current, I could slide the dot for VC, and I could get VC right here. But when I slide the dot over here on the other side, trying to make the dot on either side of one single resistor, I'm caught because I can't move the dot across here because I don't know the value of the current. Right? I can't slide this 40 up to the other side. I don't know what that dot value would be, all right, with respect to the reference. Okay, so again, I run into a problem because I can't come up with an expression using Ohm's law to figure out the current in that branch. Okay, so what would I do? Well, you could also come up with an equivalent resistance for this. The order of the elements doesn't matter in terms of the total current that shows up in that branch. Okay, and so I could combine all these. All right, so let me draw a box around them. I combine all these into an equivalent circuit. Okay, so the equivalent circuit would be, and it doesn't matter which side I put the resistor on, but 20 plus 15 is 35. All right, and then I still have the voltage source. And we've talked about equivalent resistance before. If I replace the things that are in the box with this circuit right here, then with respect to the node voltages, these circuits would perform exactly the same. Okay? And if I do that, I'm able to write node voltage equations. All right, so that's the thing that you have to do. Typically, I don't redraw the circuit. I just notice the equivalent circuit and mentally, make an equivalent circuit in my head and come up and move forward to write the node voltage equations. All right, but I'm not going to do it that way. I'm going to go ahead and redraw the circuit with equivalent circuits substituted in, and from there I can do the node voltage equations. Okay, so here's what I'm talking about. I'm going to erase this and redraw it with this equivalent circuit. So we talked about that being 35 ohms and 20 volts. Okay, so I made this substitution for that upper branch. Okay, I'm also going to erase this and replace it with its equivalent resistance. Okay, so now I have this circuit set up really pretty well for node voltage. I'm going to use this as the reference. I know this is 40 volts. I know this is VA. I know this is VB. And this is VC. So at this point, what I want to do is write node voltage equations for each unknown node. Okay? So VA, all right, so I can mark this. I'm going to put this, let me change the color so I can do each node a different color. Let's do this in purple. Okay, I mark these currents coming out. Okay, so I'm going to call this IA1, IA2, and IA3. And what do we know? By KCL, remember, node voltage is based on KCL. I have IA1 plus IA2 plus IA3 equal to 0. All right, so it's very systematic. I always draw these things coming out of the node. All right, from there, I need to decide what is the current IA1. All right, so that's where I think of pushing the dots. Okay, so here's this dot at VA. I know VA is right here on the circuit. Okay, I know this is the reference at 0 volts. So I've got the dots immediately adjacent to each side of the resistor. Right? Because I know those dot values, VA on the top dot, 0 on the bottom dot, I know the voltage across the resistor. That lets me calculate IA1. All right? I have to decide on a polarity, and I use the passive sign convention. Okay, so let me clean this up a little bit. You can see I1 is moving down, so that means this has to be plus first minus second. It's moving down according to the passive sign convention. All right, so this would be VA minus 0 divided by 35. That's IA1. Okay, now IA2. I look at IA2, all right? So IA2 is referenced in the same direction as this independent current source. So IA2 is really easy in this case. It's just 3 amps. Okay? And then finally, IA3, I look at this, my question is, where are the dots? All right? So I have a dot on one side of the 10 ohm resistor. That dot would be 40 volts, right? You slide the dot, that's 40. All right, slide the dot to the other side, that's VA. The reference would be plus and then minus based on the direction of current flow. All right, so I'm moving this way, so plus goes first, minus goes second. All right, so that would be plus VA minus 40 divided by 10. All right, so boom, I've got the KCL equation at node VA. All right, let's do this again. All right, let's do this again for VB. I'll change this to green. We're always doing KCL. All right, so for KCL, I could call this IB1, IB2, and IB3. And what I know is IB1 plus IB2 plus IB3 is equal to 0. So it's very much like we did with statics. You have these equations that apply. KCL always applies at a node. So I write down the KCL equation, and then I figure out what each of the currents would be. So I look at IB1. IB1 is referenced in the opposite direction of the independent current source. So IB1 is minus 3. Then I look at IB2. Okay, so I'm worried about my dots. Here's 0 volts, and right here on this side is VB. All right, so I track my dots down to either side of the resistor. I know Ohm's law applies. Since the current is moving down, it'd be plus on the top, minus on the bottom. So this would be plus VB over 40. VB minus 0 over 40. Okay. And you don't really need to write down the minus 0, but I like to do that just to show you where it's coming from. And if you would do that on exams, that lets me know that you know where it's coming from. All right, so I encourage you to go ahead and write down the minus 0. for exams. Okay? All right, then finally, to finish off node 3, we need IB3. Okay? So IB3, I look at the dots. On one side is VB, on the other side is VC. All right? The current goes from the left to the right. Okay, so it's moving this way. So I need a plus first minus second. So that would be VB minus VC divided by 8. Okay, so there, we're done. Boom. There's VB. Okay. All right, and finally we can move to yet a different color. I'll do this one in red. All right, so we can look at VC. All right, to get VC, I have this current, IC1, this current moving the other way, IC2. All right, moving out of the node, all right, IC3. All right, so I usually, I start over at every node and write different, a different reference current, and what I get is IC1 plus IC2 plus IC3 equals 0. All right, that's KCL, Kirchhoff's current law. Okay, so then I ask myself, what are these values? Okay, so here's the dot. This is VC. This dot right here is VC. So what is the dot right here? Well, if that's VC, I have a rise of 20, so this would be VC plus 20. All right, and then this dot is 40, so I move the dot. Here's 40. I now have the dot on either side of a resistor. That lets me calculate IC1. IC1 moves this way, so I need plus here minus here. Okay, so I can get IC1, it's VC plus 20. That's one of the dots, minus the other dot. The other dot is 40. And then I divide by the equivalent resistance, which in this case is 35. Okay, so IC1, that's probably the trickiest one for this whole circuit. All right, IC2, all right, IC2, current's measured this way. So the VC dot is right here, the VB dot is right here. It's plus first and then minus. Okay, this gets really jumbled when you write over the top of it, but you get the idea. Okay, plus first would be VC minus VB, and then the resistor value is 8 ohms. Okay, and finally IC3. All right, so IC3, I'm looking at the dots. This dot is VC, this dot is still 0, so VC minus 0 over 12. Okay, so there's the KCL equation for voltage VC, or at node VC. All right, so what I'm asking myself now is, do I have enough information to solve this problem? Okay, and what I'm seeing here is, all right, from the very first part, I have VA is unknown, and I have an equation, one equation that only involves VA, so I'm happy with that. I can solve for VA. All right, here's another equation that involves unknowns, VB and VC. All right, but then it's two unknowns, one equation. But then I look at my next equation, and I see that I have VC and VB as unknowns. Okay, so I have two equations, two unknowns that I can get. So overall, what I did was I wrote 3 node equations for 3 unknowns, and you can just plug those into some kind of equation solver or do them by hand. and you get the solution for the node voltages of this circuit. Okay, so there's part 2 for node voltage. You go back and look at that circuit, it looks like a mess, but when you take that step by step at each node, it's really pretty straightforward to write node voltage equations. You can almost do them by inspection, just write them down without doing a lot of work.